You learn a lot about famous mathematicians when you study graduate level mathematics. And that's mostly because a lot of the theorems and results are named after the mathematicians that discover them. Famous mathematicians include like Henri Lebesgue, Emile Borel, Bernard Riemann, and then I think Karl Weierstrass. I think his first name's Karl. I mostly know them by their last names, obviously, because that's how their theorems are named. And personally, I've never been big into the history of math, which might sound kind of surprising how much I studied it. Or at least that's not how I started out. I have a greater appreciation for the history of math now than I did when I was an undergrad. When I was an undergrad, I was really just interested in the results. But now I appreciate the history and the development of mathematics and, the timeline of it. And so I thought I would make a video about my favorite mathematician. My favorite mathematician is George Cantor. So I might be pronouncing his first name wrong. It looks like George, but it might be actually pronounced Georg Cantor. But I can spell it. And I am a little bit biased toward him. I'm biased toward him because when I did my thesis, I studied Cantor sets, which share his name. But I do think he's probably, of all the mathematicians I've really studied their work, I think Cantor had some of the most novel ways of proving things, maybe you can say, because he's got a lot of stuff named after him because he did things in a very unique way. Cantor lived about turn of the century, early 1900s, late 1800s, when he was doing his research. He was born in Russia, but I think he's mostly known as a German mathematician, and he lived in Germany. He is most well known for challenging the idea of infinity. So before him, there was kind of like this one notion of what infinity is, but Cantor suggested no, there's actually different types of infinity, and some infinities are bigger than others. The smallest infinity that we're all familiar with is I believe it's Aleph Null is what it's usually called, after the Hebrew letter Aleph. It is the idea of countable infinity, so these include sets that are countable. For example, the natural numbers is a countable set, the integers is a countable set, and it's kind of not immediately obvious that the rational numbers are countable, but they are countable. And he was the first one to show that the set of all real numbers is actually uncountable, which means that you have to be delicate with the definition of countability, but from an analysis point of view, the definition is you can find a bijection between some subset of the natural numbers to the set that you're interested in. So for example, the integers are countable because I can establish a one-to-one correspondence between the naturals and the integers. A set is called uncountable if no such bijection exists. So he was actually the first one to show that, okay, under this definition, you can actually show that the real numbers, or even, a smaller statement like the unit interval is uncountable. So I guess I can go through that demonstration here. So what is it? Okay, so one way that we show a set is uncountable is that we pretend for a second that it is, and then show that that's nonsense. So here's my claim. The interval from 0 to 1 is uncountable. Proof. Suppose not. Okay, so what does that mean, suppose not? It means that I can enumerate. Three. I can make a list out of them. That might be a better way of thinking of the word countable versus uncountable. Can I make a list of all the elements? And so I pretend for a second that I can. So I have the unit interval, and I can list all the elements. And now I'm going to write them explicitly. So x1 is going to be equal to 0. How do I want to say this? D11, D12, D13, D14, so on and so forth, where the D's are the digits. And then I do the same thing with x2. So I have 0.D21, D22, D23, D24. And I do that for a couple more. And I'll do one more just to illustrate my point, because I'm going to need a couple of these. 0.41, 42, 43, 4. And then this keeps going on and on and on. So I have my list. And the way Cantor showed that the unit interval is uncountable is that he did a simple, it's a famous result. It's called Cantor's diagonalization argument. And the idea here is that he just used his brain and said, okay, I'm going to make an x that's not in the list. And the way he did it was that he looked at the digits that form along this diagonal and he switched them. So for x, so he constructed a new x where it's 0 point, and then for this digit, maybe you could, add 1 to it. So if D11 was, say, 0.3, or excuse me, if D11 was a 4, he would make it a 5. And if D22 was a 2, he would make it a 3. And he would just continue on and on and on and on and on. So we get D, I don't know, 1 prime, D2 prime, D3 prime, D4 prime, yada yada yada. And it doesn't really matter if you add like 1 extra to the digit. I think as long as it's different, you're fine. Because what if the digit is a 9, for example? What would you change it to? I mean, you can change it to a 0. But you do have to be a little bit careful when you make this argument, because some decimal expansions, or it doesn't even have to be decimal, whatever base system that you're in, if it's an n-ary system, some elements will have 2 different representations, so you don't want to accidentally make it into the same representation. But it is avoidable, and I'm not going to go into the details here. But that's essentially what the argument is. You change these digits along the diagonal, and then you look at this x here, and you say, okay, does x appear in this list somewhere? And the answer is no, because it can't be x1, because D11 prime is different from D11. So these two can't be the same. And likewise, x can't be x2, because D22 prime is not the same as D22. And when you get to the nth digit in x, it's going to be different from xn at nth digit. So this x here can't possibly be in our interval. So we get a contradiction. Now, one of his famous sets that was named after him was called the Cantor set. And that's what I kind of want to talk about here. The Cantor set, I remember my thesis advisor making a big deal about when he taught us, because, I don't know, I think he just liked it. Not every analysis instructor, goes into as great detail as he did. I think he had an entire chapter in his book dedicated about countability, but the Cantor set was the belle of the ball of that chapter. So I think some of his enthusiasm rubbed off on me. So what is it? So we look at the unit interval from 0 to 1, and we decide to represent it in ternary expansion, base 3. This is one way of doing it. There's other ways of explaining it, but it's the same thing. So we have a ternary expansion, so that means D1 is equal to 0, 1, or 2. Same thing for D2, D3, yada, yada, yada. And the idea here is that we want to include all numbers that have a ternary expansion where you just have digits that are zeros and twos and no ones. So what does this set look like? We can construct it step by step. And the first step is we start with the unit interval and we can give it a name. We can call it C sub 0 for the time being. And so I divide it into thirds. And I notice that all of the points in ternary here start with 0.0. And all the points in here start with 0.1. And then all the points here are 0.2. So if I want to keep the points that have zeros and twos in the digits and no ones, I have to get rid of this middle interval. So I get rid of it. And the set that's left over makes up C1. Okay, we have to be a little bit careful though, because why is 1/3 and 2/3 retained in the set C1, but the stuff inside isn't? In other words, shouldn't 1/3 not be included? Because it's, after all, in ternary, it's 0.1. Well, actually, 0.1 in ternary, I'll write it off to the side here, is the same as 0.02 repeating. You can show this using a geometric argument, right? It's a convergent geometric series. So 0.1 is the same as 0.02 repeating. That's kind of what I mentioned earlier about decimals or ternary system numbers that have more than one representation. But we want to include this stuff. That's how we're going to define our Cantor set with this idea. Again, there's other ways to construct it, but I'm using the digit construction. So I want to include this number because it has 1 0 and a bunch of 2's, infinitely many 2's. So I want to keep it. So now I get C1. And now the game becomes do the same thing for these remaining intervals. So this is 0.00. This interval has starting digits 0.01 and a bunch of stuff, and 0.02, a bunch of stuff. And so I want to get rid of that little interval, and this is what I end up with. And a similar procedure happens over here. This is 0.20, 0.21, 0.22. We'll call this C2. And then the process continues forever. For each of these intervals I create, I divide it into thirds, and I remove the middle one every time. We'll call that C3. And you do this forever. And so the idea is that the limit of this refinement process, is what we typically call it, gives me C, which I call, or not me particularly, in mathematics it's called the Cantor set. And there are other types of Cantor sets too. It's not the only one, but it is the most famous one. To specify the one we're talking about here, we call it the middle thirds Cantor set, because we always remove the middle third. Likewise, you could remove the middle quarter and call it the middle quarter Cantor set. You could remove a big piece of it, like half of the interval, call it the middle half Cantor set. And you don't even have to put it in the middle. You can put it other places too. You can get pretty crazy with these constructions. And there are also these Cantor sets that I'm not going to explain exactly how it works, but they're called fat Cantor sets. And they're called fat Cantor sets because they have positive Lebesgue measure. And when I go through my measure theory series, and I haven't forgotten about it, it's going to be a big project, and I want to do it right, and I have something very specific in mind when I do it, and I want to do it right. But I'm definitely going to talk about that to come. But this gives me my Cantor set. And there's a very famous function that's associated with the Cantor set. It's called the Cantor-Lebesgue function. And I'm going to show you how it's constructed. And this is one of my, if not favorite, functions of mathematics. I'll put an exclamation mark just because of how much I like it. So how is it constructed? Well, all of the action happens in this square. You know what? I'm going to make it big because I'm going to need some space. So I look into the square from 0 to 1, 0 to 1. And the idea here is that these removed intervals, so this open space here, this open space here, open space here, so on and so forth, we're going to map those to some constants. Okay, so how are we going to do it? Well, we're going to construct our Cantor set on the x-axis here, x-axis. So we do this middle third. And the idea is that this removed interval from the Cantor set, this middle piece, is going to map up to 1/2. So I get a flat interval from 0 to 1/2. And now I'm going to refine my Cantor set, or I'm not refining the Cantor set, I'm constructing it. But now these two retained pieces, I'm going to divide them into thirds, and that this middle piece is going to map up to 1/4. This piece is going to map up to 3/4. Try and make sure I don't screw up my picture. So now this is what I get. And then the process just continues forever and ever. So I'm going to divide these up into thirds. And then this will go up to here, halfway point between 0 and 1/4. This one will move up to here. This piece will move up to here. This will move up to here. And then we keep doing it. And unfortunately, my picture can only be so good. But 1 will map up to 1 here, and 0 will stay at 0. And then you just keep doing this forever and ever and ever until you connect all the dots. And it doesn't necessarily look like it's going to work out and it's going to fill in these gaps, but it does. You can show that using a more formal argument of how it's done. And I'm going to reconstruct this in the measure theory series, but this is essentially the most crude way I can explain of building this function. And it's actually so popular that it even gets its own funny nickname. It's called the Devil's Staircase. Devil's Staircase. And this function has a lot of nice properties with it. Properties that you wouldn't normally expect. For example, it's continuous on a set of full measure, meaning that it's continuous on a set of measure 1. It's continuous everywhere. I should start there. It's continuous everywhere, but its derivative is equal to 0 almost everywhere, meaning everywhere except on a set of measure 0. So particularly, it's flat on all of these essentially steps of my staircase. It's flat everywhere. The only points where it's not flat is on the Cantor set, but the Cantor set has measure 0. In fact, it can be shown that this set is uniformly continuous. If I can spell. But it is not absolutely continuous. What do I mean by absolutely continuous? Well, in the real analysis language, it means that for any epsilon bigger than 0, there exists a delta such that for any family of subintervals, we'll do it this way. Make sure I don't screw anything up. So we have a family of intervals. I think that makes sense. Yep. We have the following property. We have that the sum of the differences less than delta implies that the sum of what? Of the differences of the function. So typically the well, I mean, you can call it anything really, but I'm going to call it phi here. I'm going to call the function phi x, such that phi bn subtract phi an is less than epsilon. And you can show it here, because if you pick, to show something's absolutely continuous, you show it satisfies this definition. So to show that it's not absolutely continuous, you can just find an epsilon in a collection of intervals where this property does not hold, so that the hypothesis is satisfied, but this guy here is greater than or equal to epsilon. And it's not too hard to show. You can pick some nice intervals to show that it all falls apart. So this is the Cantor-Lebesgue function. In probability theory, I believe if you have a distribution that matches the Cantor-Lebesgue function and has a special name, I think it's singular, don't quote me on it, but I think it's I believe it's called a singular distribution. So it's a weird thing. If you want to construct some weird philosophical type problems in mathematics where you have a function that is continuous on a set of cardinality equal to that of the continuum, and discontinuous on a set of cardinality also continuum, you can construct such a function using this as a building block. In fact, that was a homework problem I did recently. It was a very fun problem. I like it. So that's a few thoughts I have on George Cantor and his very famous Cantor set and Cantor-Lebesgue function. I just think this stuff is really neat. So let me know what you guys think, and I'll see you in a new video.